I'm a postdoc at Imperial College. I'm going to present today research going on in different places like Imperial College, Oxford University, and Rolls-Royce PLC about achieving the best performance possible on a variety of parallel architectures for a class of applications of computational science applications falling under the name of unstructured and mesh applications. We talk about the OP2 library, and which is our way of programming this kind of applications. So to make it fast, I just jump to the OP2 description. So I've got two slides about OP2. There is a section of OP2 calls which is about declaring a mesh, a structured mesh, and then there is the parallel computation. So this is about declaring a mesh. Whenever you want to declare a mesh, for instance, this mesh here, you have to define you can define the mesh in terms of its OP sets, which can be used to model vertices or edges, for instance, as it is the case here. You just need to tell OP2 how many edges and how many vertices in this case. You can associate data to each element in a set by using the OP data. For instance, in this example here, I'm associating the 3D coordinates to each vertex. Okay? So the last data structure is the OP map, which is the most important one because it captures the structure of the mesh. So it is used to link elements from different sets. So for instance, in this case, I'm showing you the declaration of a map between edges and vertices. So at the end of the day, what you need to pass OP2 is an array of pointers, of indices, telling, for instance, that edge 24 is connected to vertices 12 and 4. So I think I've got a pointer here. Yeah, that's useful. Parallel computation. So this kind of applications is usually applying a same user kernel, for instance, this piece of C code to every element of an OP set. So for instance, in this case, I'm trying to apply this user kernel to every edge in the mesh. So this is done by implementing a user kernel, which is only reasoning about the local edge on which it is applied. So for instance, it's taking as input a edge-related data and two vertex-related data, as well as a constant, as a global variable, actually, which is the same for all edges. And then you have to call an OP parallel loop, passing it a reference to the function, to the user kernel, the iteration set, and a sequence of what we call access descriptor that are used to bind actual parameters from the mesh data set to the various invocations, to the formal parameters of the various invocations of the user kernel. So for instance, the first line corresponds to the first parameter, and we are telling OP2 that we are going to read only this data. The edge, this is an edge data set, so it's associated to the iteration set edges, and we don't need to use any indirection, any OP map. So edge 20, when we apply the edge contribution function to edge 20, we will read the data associated to edge 20. The other two are instead using a mapping, which I call edges to vertices, very simply. And we are going to increment the two vertices. So this kernel is going to be applied to every edge, and for every edge, it's going to read the data associated to itself and increment the data associated to the two vertices in this case. So this is done by these two lines. So this 0 and 1 here capture the first and the second vertex of each edge. So the access descriptor, one of these lines, captures completely the kind of access you're going to do on the data. What's specifically important here is that the data access is completely outside the user kernel. You can't see any data access, any indirection access inside the user kernel here. So it's completely declarative here. So fundamentally, at the end of the day, what I don't want to do in my compiler is analyzing the user kernel to obtain this kind of information. So general philosophy of OP2, it's a library. It's supported in C, C++, Fortran, and most recently also Python. So it's very easy to integrate into legacy applications. You should figure out how it is possible to ask a person that's been working in Fortran for many years to now switch to a new language and re-implement completely its application. So that's why it's a library. It's an abstraction of unstructured meshes and parallel computation for multiple backend languages. So we use a source-to-source compiler to get different implementations of the parallel loops. I haven't told you that the declaration of an OP that completely transfers a data, so an array of data, into the OP2 space. There is no way from the user perspective to touch that data after declaring it without using an OP parallel loop call or get it back through other let's say, diagnostic calls. This is especially useful because we can avoid the data movement between CPU and GPU systems. I already told you about how data is accessed. So here is the general picture and some optimizations. So we've got Hydra, and so Hydra is I will talk about Hydra more later. It's a Rolls-Royce application, actually, based on finite volume. We got also this Volna application, so people are working on getting Volna on top of OP2. And we've got also a big, let's say a bigger effort to map, to compile Phoenix applications, which is a high-level, actually the name of the language is UFL. Phoenix is a set of tools to compile these UFL programs into OP2. Now, UFL is used to express, to implement in a very high level, so it's a DSL actually, partial differential equations, which are then solved using the finite element method. This specific path to OP2 passes through what we call PyOP2, which is the Python interface of OP2. Then there is a compiler. Actually, there is more than one implementation of the compiler. There is a rows-based implementation, which is a source, takes as input an OP2 program and outputs whatever you need here. So we output CUDA, OpenCL, OpenMP, MPI, and mix-ups, MPI plus CUDA, MPI alone, and MPI plus OpenMP. We have got, so the implementation of PyOP2 is actually a runtime implementation, so it's all based on runtime code generation. Optimizations, there is this standard thing to do in structured meshes, which is called renumbering, which fundamentally improves the data locality whenever you try to access the mesh data. And then we have got a different kind of optimizations depending on the target architecture. So for instance, on GPUs, we do global memory access coalescing. We do data locality through shared memory. There is also this loop fission I'm going to talk about later. On CPUs, let's say we do vectorization. We would like to do more than that. There is disparse Stalin and other kind of similar data locality improvement techniques, which might fall under the name communication avoiding algorithms. And I also implemented some loop fusion, some static-based loop fusion. So there are plenty of these. And then we have got mix-ups that depend obviously on the target architecture. So you would like to do loop fission if you're running on MPI plus CUDA, but you don't want to do that if you're running, for instance, on MPI plus OpenMP. So my idea for today was to show you the performance results of two different applications written in OP2 on different architectures. The first one is the airfoil, and the second one, so this is a simple benchmark. The second one is Hydra, so the larger application, and show you the difference. So the airfoil is let's call it a correctness and performance benchmark of OP2. It's got 5 parallel loops, which are not really complex, 60, 80. Double precision operations in a kernel, so per element, per iteration element. A very few of bytes to be staged, for instance, in the GPU implementation onto the shared memory. It's based on a 2D mesh, a two-dimensional mesh. I'm going to show you the case of 1.5 million edges. It's missing here, and 26 million edges, actually. GPU optimizations, I usually got a big slide with everything about how we optimize the GPU. I trust that you already all know these kind of things here. So we do global memory access coalescing by properly mapping thread identifiers into the corresponding global memory identifiers as much as you can. So this is based on renumbering of the mesh and having actual data locality. data locality through shared memory, in the sense that every time we access an OP data through an indirection, we first, before accessing it in the user kernel, we stage the data inside the shared memory. Okay? In OpenMP, so one of the other backends I'm going to show you is OpenMP. There are, I'm afraid, no significant optimizations, but I will surprise you later. And there is an explicit staging of indirect data, which is not hurting a lot. I also checked that the low-level compiler is capable of doing some vectorization inside the user kernel, but it's not really exciting, I'm afraid. So I'll show you also performance results for MPI alone, MPI plus CUDA, and MPI plus OpenMP for the airfoil. So let's go to these numbers. So these numbers are coming from the experiments performed by my colleague Gianni in Oxford. It's about the execution of the airfoil on a cluster of CPUs, Hector, which is this red line, and this blue line, which is a smaller cluster of Intel CPUs at Imperial College called CX1, and against a GPU cluster, this green line here. Okay, so the mesh size is 1.5 million edges, 26 million edges. Left 1.5 million edges, right 26. 3 clusters. We are distinguishing on the two CPU clusters between MPI alone, and which is the full one, the line with the full dots here, with the full points, and MPI plus OpenMP, which is the line with the empty points. Now, you can see that in both cases, actually, I need to tell you more about this, but let's pick the small mesh. In both cases, the cluster of GPUs for this kind of application is going to outperform Hector, which was at least the fastest supercomputing in the UK. You can also see that specifically this case, MPI plus OpenMP performs, scales better on Hector. So this is very promising for us, actually. And in this other case, you can see that the GPU cluster outperforms the CPU cluster, but this is not, let's say, entirely precise, in the sense that this one here actually is about using 2 GPUs instead of 1 GPU. So that's one node, the one host with 2 GPUs attached. So this line should be moved towards the right, which is still very good, actually, because this is a relatively, let's say, a modest GPU cluster against this big Cray machine. Okay, so far so good. Let's move to Hydra. So we wanted to then scale up in application complexity with a far larger application. So Hydra is used by Rolls-Royce in their production chain to simulate the turbo machinery components of their jet engines. It's a Fortran 77 application with many, let's say, beautiful programmed source code lines. It's got 1K, it's true. It's got 1K parallel loops over the mesh. Actually, I must tell you that whenever running on a GPU, we are considering the 33 loops inside the time step. So I will not consider all the 1,000 loops. The production implementation, so what they're using now, is based on the previous, the ancestor, let's call it O+ of OP2, which is an abstraction over MPI of unstructured meshes. Simulation times are very large, days or weeks. It's significantly more complex than airfoil, not only because there are more loops, but because the user kernels called by these loops are much larger, something like 600 double precision operations. And each iteration is going to need to access something like 700 bytes. So we transformed this application to use OP2, from O+ to OP2. And now the mesh is completely controlled by OP2 at the declaration time, as I told you. So it's transferred into OP2 space at the moment of declaration. And we obtain this no data movement between the host and the device, which we actually wanted. So I think the next one is the performance results. So again, I forgot to tell you before. So usually in my graphs, smaller is better, so low is better, okay? So we are comparing here the scaling of Hydra using O+, old implementation, on MPI, on a single node, actually it's a node with 2 CPUs, against Hydra executing straight lines on the GPU. So the GPU is a NVIDIA CS2070. The two CPUs are in Intel Westmere, 2 Intel Westmere with 6 core each, so 12 processes. We will use up to 12 processes here, and a Sandy Bridge with 4 cores. So the first thing that I did is converting Hydra to OP2, run it through the compiler, debug, and I got this line here. So first implementation of OP2 on a GPU didn't even reach 4 cores of an Intel multi-core, which was quite bad for me. So after a while, I analyzed the performance of this application, and I discovered that there were some loops which were behaving particularly bad. And I was able to move this line down here. Now, my hypothesis is that by automatizing this kind of optimizations inside the OP2 compiler, I will be able to push down this line even more. But again, if I'm going to focus on this line in OP2, I will be able to push down that line for Intel, in this case, multi-cores even down. So this is something like a race towards the best performance possible, as I told you at the beginning of this presentation. So the performance analysis told me that there are 6 loops over 33 which are specifically bad in the sense that they hit the 2 problems, let's say the 2 limitations of a GPU, which is a limited amount of shared memory and a limited amount of registers per thread. In this graph, I'm focusing on the shared memory thing. You can see here the partition size, and the different lines here are different loops. These are the names of the loops, which are not really important. Shared memory in the y-axis. You can see this red line here, which is the limit of the GPU, of the NVIDIA GPU, the C2070 GPU. And you can see that I'm forced to run with small partition sizes here for most of the loops. So this means, at the end of the day, that I don't have enough parallelism to mask the global memory access latencies, okay? So my idea was, okay, let's make these loops simpler. By making these loops simpler, I'm going to reduce also the number of registers needed by the simplified loops. So this can be done in this way. I don't want to insist on this thing because I don't have time, actually. It was about splitting, actually fissioning a loop. So if we have a loop like this over edges, so we consider all the edges in the mesh, and we compute some contribution, and then we apply the same contribution to the left, your left, and to the right vertex, then we can think about splitting this single big loop with a big user kernel into 3 loops. They all iterate again over edges, but now the first loop computes the contributions and stores them into the global memory, the global GPU memory. The second one is going to access the same contributions computed by the first loop, and it's gonna increment all the left or right vertices of each edge. And the third loop will update the remaining vertex. Now, this simple thing can be currently done automatically in OP2 without analyzing the user kernel. If we want to split even more these, so get also better performance, we need to split the contribution calculation here, which requires a user kernel analysis. To focus on 4 of the most complex loops of Hydra, you can see that this is the execution time in red before splitting. This is the execution time after splitting. You can see between 15 and 55% performance improvement. So that's the right way to go for CUDA. I got this slide about composing up things, Hydra on single node, so either GPU, this line here, and so on single node, multiple GPUs, 1 GPU and 2 GPUs, and so MPI plus CUDA, it's the case here. And also OP2 compiling to OpenMP, the yellow line, and compiling to MPI without anything else, so sequential nodes. So our process is mapped to a core, and that's completely sequential. There are 2 lines here for MPI plus sec, one with no smart renumbering, and the other one with smart renumbering, which is the red one. O+, so the old implementation of Hydra, again outperforms, not by much. So we are slowly going there. We are slowly getting there, specifically after renumbering. So This is something like the interesting bit about OP2, so we can get, let's say, comparable, and it will be very near to or better than this performance very soon on a variety of parallel architectures. A small notice here, I got an OpenMP, an additional OpenMP, which is not shown here, which is compiling the same application, OpenMP, without vectorization. Now, this is an Intel Westmere, again, with 12 cores. It's got only SSE 4.2, so it's not very different. I'm talking about what the Intel compiler is capable of vectorizing inside the user kernel. Have I got time? No. 2 minutes. So I got this slide about OP2 vectorization. I'm going to go very fast over it. So I was talking about vectorizing inside the user kernel, where the alternative is vectorizing across the iterations. Now, if this is simple, because we hope that the Intel compiler will be able to vectorize inside the user kernel affine loop nests, this is not simple, because we are, you remember, you are accessing data through pointers. So we need to do something like called let me go directly here, gathering the data into the vector registers, which is the complex thing to do. But at the end of the day, it's not really different from what we do in Hydra, in CUDA, with the shared memory. So we implemented this gathering. So we access, when we are iterating over edges, we access vertex data. We gather this data, this different data through access through pointers here, into the vector registers. And then we, let's say, do something more to get vectorization, which is using the Intel vector support, if I can remember it well, in Fortran. So what we do is fundamentally doing on a user kernel, doing the scalar and array promotion, which is fundamentally transforming the user kernel from operating on a single iteration to operating, in this case, over, let's say, 4, because we were running on AVX, over 4 iterations. So this is a simple transformation that we can do easily in the compiler. And we obtained this performance for the airfoil, which is the 3 indirect loops. I'm talking about indirect loops because for direct loops, an Intel compiler is fine. It vectorizes across iterations. I'm talking about these 3 indirect loops, and we got 38%, 20, and 12% performance improvement, including the gather cost, so the cost of gathering data from main memory into the vector registers. So this is a thing that we want to push, actually. Conclusions. This is a sentence from my boss, Paul Kelly. Unstructured and mesh applications have been on the massive frontier of the compiler research for a long time. There are many optimization opportunities out there to try. It's a complex enough problem, but not completely regular, so we can still do many things here. We would like, this is my holy grail, to define some optimizations which could be eventually moved back to more structured cases. It's definitely something that we need to target if we want to accelerate industrial applications. Thanks to Rolls-Royce to give us their code, actually, and the TSB and IPSERC that are funding the OP2 project. And I think these are the pointers, and this is my last slide. Thanks very much.
And well done for getting us back on track. Sorry to squeeze you, but you did brilliantly. Well done, thank you. So we do have a minute or two for any questions. Any questions for Carlo? Somebody must have one somewhere. I had one myself, which was, so one of the benefits of this approach must be that with the new library, the code might be simpler than if you wrote it all by hand with MPI. So the O+ version of the code that you're comparing to is still a little bit faster than your new code, but your new code should be a lot simpler and easier and fewer lines. And
that's unfortunately not true, because there is no single line of MPI in Hydra. O+ is a complete mask over MPI, so it's a complete abstraction. And I mean, it's not like I'm fighting against someone here. It's the same library, but just revisited and redefined. So yes, we do hope to get exactly the same performance. There is no evidence why we should not.
Okay. Were there any more? There was one probably slightly closer to your side over there.
Thank you. I just wanted. I was a little confused about what you meant by an iteration. You implied that you could run iterations in parallel, but is there no dependency between them? What are you meaning by an iteration?
The definition, you're right. I completely skipped that part because I didn't have time. So the definition of a parallel loop is that the order of the iterations must not influence the final result of a parallel loop. That means that yes, there might be two edges trying to increment the same vertex because they are connected to that vertex, but I can run them, let's say, in whatever order I like. So what OP2 does, it depends on the target on the back end. So in MPI, we replicate the execution of those two edges on two different processes. In a GPU, we color the mesh and we give two different colors to the two edges, and we run. We execute the iterations, so the edges following colors. So this one will be never executed with a neighbor.
I see. Thanks.
Time for one last question, if there's any more. No? Okay. Well, let's thank Carlo again. Thank you very much.